I thank the organizers for giving me the opportunity to speak, and I thank the audience members for listening to me. The title of my talk is Rank 1 Phenomena in Convex Projective Geometry, and it is based on the paper Rank 1 Hilbert Geometries. Our goal in this talk is to study linear non-Gromov hyperbolic groups gamma. In particular, we will focus on groups gamma, which are subgroups of PGLTR and which satisfy an extra geometric property. Namely, gamma acts by automorphisms on special subsets omega of the projective space called properly convex domains. The plan for the talk is to develop an analogy between the geometry of properly convex domains and the geometry of Cat0 spaces, and then to introduce the notion of rank 1 for gamma and omega as above. Then we will characterize the elements in gamma that capture the essence of hyperbolicity by using concepts from geometric group theory. And finally, we will use these hyperbolic elements to understand the structure of gamma. The backdrop for this project is a result by Yves Benoit, where he showed that if omega, in addition to being a properly convex domain, is strictly convex and omega mod gamma is compact, then the quotient manifold omega mod gamma has properties resembling Riemannian negative curvature. We want to understand and generalize this correspondence to more general properly convex domains on one hand and Cat0 spaces on the other. The motivation for trying to understand and define a notion of rank 1 in convex projective geometry is the success that has been obtained in the study of rank 1 phenomena in Riemannian non-positive curvature and in Cat0 spaces. For example, the rank rigidity results, which have been proven in the Riemannian non-positive curvature case and which have been conjectured in the case of Cat0 spaces. Let me begin with some definitions. An open subset omega of the projective space is called a properly convex domain if omega is a Euclidean bounded convex domain in some affine chart. So for example, the picture given in this slide is an example of a properly convex domain in RP2. For some choice of affine chart, it looks like this Euclidean bounded convex domain in R2. Hence, it is a properly convex domain in RP2. Partial omega denotes the topological boundary of omega. In this figure, it is this black curve which bounds omega. Any properly convex domain omega can be equipped with the Hilbert metric, which is defined using cross ratios. Given any 2 points x and y in omega, we can look at its image in the affine chart and take the Euclidean line that passes through x and y that will intersect the boundary of omega at 2 points a and b. Taking the cross ratio of those 4 points and taking its logarithm defines a distance on omega. And this is what the Hilbert metric formula is. The projective lines in omega are geodesics for the Hilbert metric. However, depending on the shape of omega, there could be many more geodesics between any 2 points. We will revisit this point in a future slide. The automorphism group of omega consists of all projective transformations which preserve omega. Since projective transformations preserve cross ratios, the automorphism group of omega is a subgroup of the isometric group of omega. Now let us look at some examples. The picture on the left is a disk in RP2, and the disk with its Hilbert metric is isometric to H2, the Riemannian manifold of constant curvature -1. The picture on the right is a triangle in RP2, and this triangle with its Hilbert metric is quasi-isometric to R2. So triangle in RP2, or in general simplices in RPN, are models for flats in convex projective geometry. There are also other examples called higher rank symmetric domains, which are projective analogs of higher rank Riemannian symmetric spaces. One of them that I'm going to describe now is POS N, the set of all positive definite symmetric n by n matrices normalized to have trace 1. POS N is a projective model for the symmetric space SLNR mod SON when n is bigger than or equal to 3. Similar models exist for SLN complex numbers, SLN quaternions, etc. I'm not going to describe all higher rank symmetric domains, but for the purpose of this talk, it is enough to remember that these higher rank symmetric domains exist, and they are projective analogs for higher rank Riemannian symmetric spaces. Let us now revisit the question of geodesics for the Hilbert metric. Here we have a triangle in RP2, and in the given figure, the broken projective geodesic that goes from X to Z and then from Z to Y is a geodesic between X and Y because it realizes the distance between X and Y. In fact, all the red dotted lines that you can see in this figure are geodesics between X and Y. So this shows that there are projective domains like the triangle here where the geodesics between points are not unique. In general, given a properly convex domain, geodesics are not unique and the distance function is not convex. Hence, these spaces are not CAD0. Thus, the question of developing an analogy between the geometry of omega and the geometry of CAD0 spaces is indeed non-trivial and interesting. Because these spaces do not have unique geodesics, we will set apart a class of geodesics that we will be referring to quite frequently during the talk. So we set up this convention that whenever we see closed bracket xy, we mean the projective line geodesic that goes between x and y. And whenever we see open bracket xy, we mean the projective line geodesic between x and y minus its endpoints. Let me also standardize some notation that will be necessary going forward. Omega will always be a properly convex domain. Gamma will always be a discrete subgroup of the automorphism group of omega. If gamma is an element in automorphism group of omega, then gamma tilde in GLDR denotes its lift of unit norm. If V is a point in the projective space, then V tilde in R to the D denotes its lift of unit norm. If gamma tilde is a matrix in GLDR, then lambda 1 through lambda D denotes the absolute values of the eigenvalues of gamma tilde arranged in decreasing order. Let us also introduce the symbols gamma plus and gamma minus. Gamma plus is a point in omega closure, which is an eigenvector for the matrix gamma tilde corresponding to an eigenvalue of maximum modulus. Similarly, gamma minus is a point in omega closure, which is an eigenvector for the matrix gamma tilde corresponding to the eigenvalue of minimum modulus. Now we are in a position to start discussing the main results of this talk. I will first define the notion of rank 1, and I begin by introducing the definition of a rank 1 automorphism. Gamma in the automorphism group of omega is called a rank 1 automorphism provided lambda 1 of gamma tilde is bigger than lambda d of gamma tilde, where gamma tilde is a lift of gamma. The second condition is that gamma has an axis. That is, there is a point gamma plus in the eigenspace corresponding to lambda 1 and a point gamma minus in the eigenspace corresponding to lambda d, so that if we take the line segment joining gamma plus and gamma minus, then it is entirely contained in omega. And the third condition is that none of these axes of gamma are contained in a half triangle. I have not defined half triangle rigorously. Rather, I want to explain it using pictures here. If you look at the bottom right corner of the screen here, there's a picture that is labeled not allowed. If you look at that picture, then the axis between gamma plus and gamma minus, which is marked out in red, is geometrically contained in a half triangle. What I mean by that is, if you look at the top half of that picture above the red line, then gamma plus, z, and gamma minus determines half of a triangle that contains the axis. This is something that we do not want to see for a rank 1 automorphism. If you look at the other picture there, which is labeled allowed, in that picture, the axis between gamma plus and gamma minus, if you look at either side of it, you do not see a half triangle. So this is something that we are going to allow. This is basically what the third assumption is all about. Now, this half triangle assumption might look artificial in the beginning, but I want to emphasize that it is motivated by the CAD0 definition of a rank 1 isometry. In CAD0, an element is said to be rank 1 if its axis is not contained in a half flat. And since the projective analogs of flats are triangles, it is only natural to replace a half flat by a half triangle. Going back to the definition, if gamma is a discrete subgroup of the automorphism group of omega, then we are going to say that gamma is a rank 1 group if it contains a rank 1 automorphism. With this definition of rank 1 automorphism, we can prove some interesting properties for a rank 1 automorphism right away. We have listed them here as proposition 1. First, we can show that gamma is biproximal, that is lambda 1 is bigger than lambda 2, lambda d minus 1 is bigger than lambda d, and gamma tilde, which is a lift of gamma, has this form of a block matrix. In this matrix, the middle block A has this property that the largest eigenvalue of A is less than lambda 1 and the smallest eigenvalue of A is bigger than lambda d. The second conclusion is that gamma has a unique axis. Recall that when we defined the axis of gamma, we had just demanded that it could be any projective line segment passing through omega that goes from a point gamma plus in the largest eigenspace to a point gamma minus in the smallest eigenspace. The third conclusion is that the fixed point set of omega intersect omega closure is exactly gamma plus and gamma minus. So if we pick any other point z from the boundary of omega, then that z is not a fixed point. This gives us north-south dynamics. What I mean by that has been explained in the picture at the bottom of the slide. Because z is not a fixed point, if I look at gamma to the n z or gamma to the minus n z, it converges to gamma plus or gamma minus respectively. The fourth conclusion is that if z is any point in the boundary different from gamma plus or gamma minus, then the line segment joining gamma plus to z and z to gamma minus is contained in omega. So any line segment that lies in omega closure and starts at gamma plus or gamma minus passes through the interior of omega. For this slide, we assume that omega mod gamma is compact, or more generally, convex co-compact. Under the assumption of convex co-compactness or compactness, we can show that gamma being a rank 1 automorphism is equivalent to gamma being biproximal and gamma having an axis in omega. The benefit of having this proposition is that the half triangle condition in the definition of rank 1 is harder to verify in concrete examples, whereas the condition of biproximality and having an axis in omega is relatively easier to check. Here's an application of proposition 2. Benoit used Coxeter groups to construct examples of non-Gromov hyperbolic 3-manifold groups. One can use computers to check that these Coxeter groups contain biproximal elements which have an axis in omega. So these examples constructed by Benoit are rank 1 groups. This shows that the class of rank 1 groups is larger than the class of Gromov hyperbolic groups acting on properly convex domains. And it also shows that the rank 1 properly convex domains is a larger class than strictly convex domains. There are more examples of rank 1. If gamma is a relatively hyperbolic group that is not free abelian, and gamma acts convex co-compactly on omega, then gamma is a rank 1 group. In fact, here's a remark. For such a gamma, omega is going to be a properly convex domain with isolated simplices. This isolated simplices is a geometric condition that was introduced in a joint work by Andrew Zimmer and myself, and it is analogous to the isolated flats condition in CAT0. There are some prominent non-examples of rank 1 group on the other hand. They are number 1, the free abelian groups, and number 2, if gamma is a lattice in SLNR or SLNC when n is bigger than or equal to 3. Now, the reason why these are non-examples will be proven later on as an application of the theorems that we developed during the course of this talk. Now we introduce the notion of closest point projection onto a rank 1 axis. This notion will help us connect the notion of rank 1 that we have introduced with the notion of hyperbolicity coming from geometric group theory. If L is a projective line segment in omega, then we say that L is a rank 1 axis provided It is the axis of some rank 1 automorphism gamma. Given a rank 1 axis L and a point x in omega, we define this set of all points y in L which are closest to x. Now this set does not need to be a singleton. However, the convexity of omega forces this set to be a certain interval Ix, which is contained in L. So the way we define the closest point projection map pi L is by doing the following. Given any point x in omega, we map pi L of x to be the midpoint of Ix. With this definition of closest point projection, we now arrive at a point where we can define what contracting elements are. This is a notion from geometric group theory. In geometric group theory, there is a philosophy that contraction properties capture an essence of hyperbolicity. We will use the notion of contraction due to Alex Sisto. Some other notions of contraction that can be found in the literature, like the one due to Bestvena and Fujiwara, will be equivalent in the context where we are working. So now if we take the definition of contracting element defined by Sisto and interpret it in our context, then this is what the definition looks like. One, our element needs to be infinite order. Two, if we fix a base point P in omega and look at the image of the subgroup generated by gamma under this orbit map, then we will get a quasi-geodesic AP. And three, there is a coarse projection pi AP that maps omega to AP, and there's a constant C positive so that the conditions 3A and 3B are satisfied. Condition 3A basically says that the coarse projection map pi AP is coarsely identity on the set AP. The condition 3B is quite cumbersome, the way it has been written out or the way it is rigorously defined. So I suggest that you please follow me onto the next slide where there is a picture describing the condition 3B. Here's the picture describing the condition 3B. It says that given any 2 points x and y in omega, look at its projections pi x and pi y on AP. Either the distance between those projections is bounded by C, or those projections are really far apart, in which case there is a point x prime and there is a point y prime on the geodesic between x and y, such that the distance between x prime and pi x is bounded above by C, and the distance between y prime and pi y is at most C. So in a way, it is saying that given any 2 points, either their projections are really close, or the geodesic between those 2 points spends a lot of time close to the quasi-geodesic AP that we get from looking at the orbit map. Here are some examples of contracting elements. Hyperbolic elements in relatively hyperbolic groups, pseudo-anosov elements in mapping class groups, and rank 1 isometries in CAD0 groups. Thus, we see that contracting elements characterize hyperbolicity in many different contexts. Now we are in a position to state the main theorems of this talk. Theorem 1 says that the automorphism gamma in the automorphism group of a properly convex domain omega is rank 1 automorphism if and only if it is contracting. This theorem has a parallel in the CAD0 world where Sisto proved that a CAD0 isometry is contracting if and only if it is a rank 1 isometry in the CAD0 sense. Now, using theorem 1, we can establish a connection between acylindrical hyperbolicity and the rank 1 condition that we have developed. Acylindrically hyperbolic groups were introduced by Osin as a generalization of the notion of chromohyperbolic groups. Prominent examples include relatively hyperbolic groups, most mapping class groups, outer automorphism group of free groups, rank 1 proper co-compact CAD0 groups, and so on. Let us also recall that a discrete subgroup gamma of the automorphism group of omega is said to be rank 1 if and only if it contains a rank 1 automorphism. In theorem 2, we can show that if gamma is a rank 1 group, then either gamma is virtually cyclic or gamma is an acylindrically hyperbolic group. This theorem also has a parallel in CAT0, where we see that the same theorem holds true for proper action of a group G on a proper CAT0 space. Now, theorem 2 is interesting because of two reasons. First, it adds the rank 1 groups from convex projective geometry to this long list of acylindrically hyperbolic groups. Secondly, we can use all the results that have been proven for acylindrically hyperbolic groups to prove new and interesting applications in the world of convex projective geometry. This is what I'm going to spend the next few minutes doing. The first application that we have is in computing the second bounded cohomology. If F is a map from the group gamma to R, we will say that F is a quasimorphism if F satisfies this equation coarsely. This equation you can see right there. In the second line is the equation for a group homomorphism, and F is a quasimorphism if it satisfies that equation coarsely. QH tilde gamma R is the set of all quasimorphisms of the group gamma, and the interpretation of QH tilde is that it is the kernel of the comparison map that goes from the second bounded cohomology of gamma to the second cohomology group of gamma. We can show that if gamma is a torsion-free rank 1 group that is not virtually cyclic, then the dimension of QH tilde is infinite, and hence the dimension of the second bounded cohomology group of gamma is infinite. Instead of looking at cohomology with coefficients in R, we can look at cohomologies with coefficients in a uniformly convex Banach space like LP gamma when P is between 1 and infinity, and similar conclusions will be true in that case as well. A corollary of this proposition is that if gamma is a free abelian group, or if gamma is a torsion-free lattice in SLNR or SLNC for n bigger than or equal to 3, then gamma is not a rank 1 group. The reason for that is when gamma is free abelian or when gamma is a lattice, the dimension of their bounded cohomology groups have been computed, and we know that those dimensions are 0. So the proposition here shows that such gamma cannot be a rank 1 group. We have more applications. We can show that a rank 1 group that is not virtually cyclic is SQ universal, which means that such groups have lots and lots of normal subgroups. The only Baumschlag solitary group that is a rank 1 group is the free group on 2 generators. We have more applications that show that rank 1 automorphisms are generic in different senses. The first one is genericity in the sense of random walks, where we can show that if gamma is a rank 1 group that is not virtually cyclic and xn is a simple random walk on gamma, then probability that the random walk does not end up at a rank 1 automorphism after n steps decays exponentially in n. We also have genericity in terms of Zariski density, where we show that if omega mod gamma is compact and omega is not a higher rank symmetric domain, and we also have a technical condition on the limit set of gamma in the projective space, then the set of rank 1 isometries in gamma is Zariski dense. I began my talk citing rank rigidity results as a motivation for coming up with a definition of rank 1 for properly convex domains. So I will conclude my talk with a discussion about the status of the rank rigidity question in convex projective geometry. In a recent work, Andrew Zimmer proved a higher rank rigidity theorem for properly convex domains under some assumptions. If omega is irreducible and omega mod gamma is compact, then it follows from Andrew Zimmer's work that his definition of higher rank and my definition of rank 1 are exactly complementary to each other. So for any such group gamma, either the group gamma is rank 1 or omega is a higher rank symmetric domain and gamma is a higher rank lattice, provided we have the assumptions that omega is irreducible and omega mod gamma is compact. So there is a conjecture now. I will attribute this conjecture to Andrew Zimmer and my advisor Ralph Spazier, and the conjecture says that this is also true in the convex co-compact case. And with that, I conclude my talk. All the details can be found in the paper Rank 1 Hilbert Geometries on the archive. Thank you for listening to me.